Picture this: you are standing in a museum, gazing at an ancient Egyptian artifact. It might be a fragile bead from a funerary necklace, a painted panel from a sarcophagus, or a small, exquisite statue of a god. It has survived for thousands of years, yet the color is not a faded whisper of the past. It is a brilliant electric blue, a shade so vibrant, so impossibly alive, it seems to glow with an inner light, defying the crushing weight of centuries. It feels less like a relic and more like a message, a direct line from a civilization that mastered the impossible. This is not just any blue. This is Egyptian blue, the first synthetic pigment ever created by humankind, and its story is one of the greatest technological secrets of the ancient world. What you are looking at is more than just paint. It is a frozen moment of genius, a chemical recipe so advanced that its full brilliance would not be understood again for millennia. The ancient Egyptians were obsessed with color. For them, it was never merely decorative. It was symbolic, magical, and deeply spiritual. They saw the world through a lens where every hue held power. Green was the color of life and resurrection, represented by the lush vegetation that sprang from the Nile's black soil. Red was the color of chaos and desert. But blue was the color of the heavens, the home of the gods. It was the color of the sacred lapis lazuli stone, a rare and precious commodity that had to be hauled from distant mines in Afghanistan. To cover vast temple walls, to paint the tombs of pharaohs, to adorn countless sacred objects with the divine color of the sky, they needed a blue that was not just symbolic but accessible. They needed to manufacture the heavens themselves, and so, in a feat of early chemistry that seems almost alchemical, they did. They learned to create their own sky, their own divinity in a furnace. This video is a journey into that fire. We are going to unravel the secret behind the Egyptian blue pigment, a secret that was lost for over 1,000 years. We will explore the sandy workshops where artisans became chemists, meticulously combining sand, copper, and an alkali flux to create a crystalline substance that would captivate the world. We will follow the trail of this incredible pigment as it traveled across the ancient world, from the palaces of Rome to the villas of Pompeii, prized by empires that came after. And we will discover how modern scientists, using tools the Egyptians could never have dreamed of, have recently uncovered even more astonishing properties of this ancient color properties that are pushing the boundaries of modern technology. This is a story of artistry meeting science, of a lost knowledge that is only now revealing its true potential. So let's step into the world of the ancients and discover how they captured a piece of the sky and made it eternal. So what exactly was this miraculous substance they cooked up in their kilns? At its heart, Egyptian blue is a testament to ancient innovation, a man-made crystal engineered for beauty and endurance. Chemically, it's known as calcium copper silicate. Now, that might sound complex, but we can break it down into the surprisingly simple ingredients those early chemists would have recognized. They started with three main components: a source of calcium, which was often crushed limestone or even seashells, a copper mineral like malachite, and a special type of sand rich in quartz. These raw materials were then mixed with an alkali flux, something like natron, a salt harvested from dry lake beds, which acted like a helper to drastically lower the melting point of the entire mixture. This specific combination was heated in a furnace to a scorching temperature, somewhere between 800 and 900 degrees Celsius. This intense heat wasn't just melting the ingredients, it was facilitating a profound chemical reaction, fusing them together to grow tiny, flat, rectangular crystals. This unique crystalline structure is the true secret to the pigment's genius. Each of these microscopic crystals acts like a perfect, minuscule trap for light. They absorb the red and green wavelengths of light and then emit or reflect back that stunning, resonant blue we see. This is why the color is so intense and why it retains its vibrancy even after thousands of years exposed to the elements. The crystal itself is incredibly stable, resistant to fading from sunlight, and largely impervious to mild acids and weather, unlike many organic pigments derived from plants or insects. To truly appreciate this achievement, we need to contrast it with what else was available. The only other blue the ancient Egyptians had access to was the phenomenally expensive powdered lapis lazuli, which had to be imported from a single source thousands of miles away. Or they had azurite, another copper-based mineral, but its color was weaker and it was notoriously prone to turning green over time as it reacted with the air. Egyptian blue was their solution to a very practical problem. It was a democratization of the divine. By creating a synthetic alternative that was not only more affordable but also significantly more brilliant and durable than its natural counterparts, they unlocked the ability to paint the ceilings of entire tombs to mimic the night sky, to color the headdresses of gods and pharaohs on a scale previously unimaginable. They weren't just making a new color, they were engineering a new reality, capturing the essence of the sky in a jar. To understand the sheer magnitude of this innovation, we need to step back and look at the painter's palette of the ancient world before Egyptian blue entered the scene. For millennia, artists were at the mercy of nature. Their colors were fleeting, inconsistent, and often perilously difficult to obtain. Reds and yellows could be coaxed from iron-rich clays and ochres, which were relatively stable. But the realm of blue was a landscape of frustration and longing. The most coveted blue was, of course, lapis lazuli, that stunning deep ultramarine stone that had to journey thousands of miles from the remote mountains of Afghanistan. It was so incredibly rare and expensive that its use was reserved for the most sacred of objects, a luxury item for depicting the gods and the pharaohs themselves. Then there was azurite, a copper carbonate mineral that offered a lighter sky blue hue. But azurite was fickle. Exposed to moist air over time, it would gradually undergo a chemical transformation, turning a dull, sickly green as it converted to malachite. Beyond minerals, there were organic dyes derived from plants like woad or insects, but these were notoriously fugitive, fading dramatically when exposed to light. An artist could spend weeks on a masterpiece, only to watch its most vibrant elements vanish before their eyes, a tragedy of impermanence. Against this backdrop of scarcity and instability, the invention of Egyptian blue around 2500 BCE must have felt nothing short of miraculous. It wasn't a gradual improvement, it was a quantum leap. For the first time in human history, a color was not found or extracted. It was engineered. This was not alchemy in the mystical sense, it was applied material science. The ancient Egyptian artisans, likely working in temple or royal workshops, had discovered a way to create a perfect, durable, and brilliantly colored crystal through a controlled chemical reaction. They determined the precise ratios of sand, copper, limestone, and alkali. They mastered the exact temperatures needed in their kilns, a process requiring incredible skill and observation without the aid of modern thermometers. The result was a pigment that could be produced reliably in potentially vast quantities right there on the banks of the Nile. This revolution cannot be overstated. It fundamentally changed the artistic and cultural landscape. Suddenly, the color of the heavens was no longer a scarce resource locked away in a distant land. It was a local product. This democratization of the divine color meant that it could be used on an entirely new scale. Entire temple ceilings could be painted a brilliant blue to represent the sky goddess Nut. Tomb walls could be filled with elaborate scenes under a permanent, unwavering azure sky. Statues, jewelry, and even cosmetics could be infused with this sacred hue. The pigment's dominance was so complete that it became the blue of the Mediterranean world for over 3,000 years. Its use spread from Egypt to Mesopotamia to the Minoans on Crete, and eventually to the heart of the Roman Empire, where it was known as caruleum and used to paint the walls of lavish villas in Pompeii. It remained the premier blue pigment until the fall of Rome, when the intricate knowledge of its production was seemingly lost, fading into obscurity like the organic dyes it had once superseded. For centuries, this radiant blue from the sands of Egypt would remain a technology without an instruction manual, a secret waiting to be rediscovered. So how did they turn these humble, earthbound materials into a pigment that seemed to capture a sliver of the sky? The process was a masterclass in early materials engineering, a carefully choreographed dance of heat and chemistry. We can reconstruct the steps thanks to modern analysis of ancient slag heaps, residue found in crucibles, and even texts like those from the Roman architect Vitruvius, who documented the recipe centuries later. It all began with gathering the four crucial ingredients. First, the silica, which came from quartz sand, but not just any sand. It had to be clean and free of impurities that could muddy the final color. Second, a source of copper. This could be a crushed copper ore like malachite, which is a beautiful green stone, or sometimes even bronze filings, the scrap metal left over from crafting tools and weapons. Third, calcium carbonate, which was readily available as crushed limestone or even powdered seashells. And finally, the secret ingredient that made it all work, an alkali flux. In Egypt, this was almost always natron, that special salt they also used in mummification, harvested from the dried beds of lakes. These ingredients weren't just tossed into a pot. They were meticulously ground into fine powders using stone mortars and pestles, then mixed together in very specific proportions. Getting this ratio right was everything. Too much copper and the color could turn murky, too little and it might not develop that signature blue at all. This homogeneous mixture was then placed into a ceramic crucible, a small, durable pot designed to withstand incredible heat. The crucible was then loaded into a kiln, which was likely fueled by charcoal to achieve the necessary intense and consistent temperature. The firing was the most critical phase. The kiln had to be heated to somewhere between 850 and 950 degrees Celsius for a sustained period, often several hours. This is a dazzling orange heat, far hotter than what's needed for ordinary pottery. The artisans had to maintain this temperature without the aid of any modern thermometers, relying solely on their experience and the color of the fire itself. Inside the crucible, the alkali flux performed its magic. The natron acted as a catalyst, drastically lowering the melting point of the silica sand. This allowed the entire mixture to fuse together at a lower temperature than sand would normally melt at. During this prolonged heating, a complex chemical reaction took place. The copper ions from the malachite or bronze infiltrated the molten silica lattice, and in the presence of the calcium from the limestone, they began to form those perfect, flat crystals of calcium-copper silicate. After the firing was complete, the kiln was allowed to cool slowly. What remained was not a liquid but a solid, glassy cake, often blue but sometimes a dullish color on the outside. This cake was then broken up and ground into the finest possible powder, just as one would grind grain. The finer the grind, the lighter and more brilliant the blue became. This powder was the finished product, ready to be mixed with a binder like egg white or gum arabic to create a paint that would last for millennia. It was a process that demanded not just artistry, but a profound, hard-won understanding of the very elements themselves. Now, to truly appreciate the genius of this pigment, we need to peer into its very structure, down to the molecular level where the magic of the color actually happens. Think of the finished Egyptian blue powder not as a simple dye, but as a matrix of countless perfectly formed miniature crystals. Each of these crystals is a calcium-copper silicate, and their flat, plate-like shape is the first key to their brilliance. When light, which is composed of a full spectrum of colors, strikes the surface of a painted object, it interacts with these crystals in a very specific way. Inside the crystal lattice, the copper ions are trapped within a cage of silicon and oxygen atoms. These copper ions are the star performers. They have a unique appetite for certain parts of the light spectrum. They eagerly absorb the warmer wavelengths, the reds, oranges, and yellows. But they have no use for the blue light. That specific wavelength of blue is rejected, reflected back outwards towards our eyes. It's this selective absorption and reflection that gives the pigment its unmistakable resonant hue. The more uniform and well-formed the crystals, the more efficient this process becomes, resulting in a purer, more intense blue. This crystalline structure is also the secret to the pigment's legendary durability, its resistance to fading, which we call lightfastness. Many organic pigments, like those made from berries or insects, have complex molecules that are easily broken down by the energy in ultraviolet light. Over time, this bombardment from the sun essentially bleaches the color molecules, causing the pigment to fade. But the structure of Egyptian blue is fundamentally different. The bonds holding the calcium, copper, silicon, and oxygen atoms together are incredibly strong ionic and covalent bonds, forming a robust mineral-like lattice. This lattice is so stable that the energy from sunlight is simply not enough to break it apart. The color is locked into the very architecture of the crystal itself. You could leave an object painted with Egyptian blue in the desert sun for centuries, and while the binder holding the pigment to the surface might deteriorate, the blue crystals themselves would remain chemically unchanged, their color as vibrant as the day they were fired. Furthermore, this robust structure grants the pigment remarkable chemical stability. Unlike its natural cousin azurite, which slowly reacts with moisture and carbon dioxide in the air to form a green patina, Egyptian blue is largely inert. It is resistant to mild acids and alkalis, meaning it wouldn't be easily damaged by the elements or even by the slightly acidic conditions that can form over time in a sealed tomb. This is why when we uncover these artifacts today, the blue is often the most well-preserved color on the palette. The greens may have faded, the reds may have dulled, but the Egyptian blue remains, a stubbornly brilliant echo of the ancient artist's intent. In essence, the ancient Egyptians didn't just create a color, they engineered a microscopic, permanent light filtering system. They built a durable, self-contained universe within each tiny crystal, one designed to capture warmth and radiate an eternal, celestial coolness. The physical proof of this vast, organized industry lies scattered in the sands of Egypt, waiting to be read like the pages of a technical manual. For decades, archaeologists have pieced together the evidence, and the picture that emerges is not of a few lone artisans, but of a sophisticated, state-sponsored manufacturing network. Two sites in particular offer a stunningly clear window into this world of ancient mass production: the royal city of Amarna and the delta capital of Pi Ramesses at Cantir. At Amarna, the short-lived capital of the pharaoh Akhenaten, excavations have revealed workshops dedicated to the production of materials for the elite. Here, archaeologists uncovered not just finished objects, but the entire messy industrial process frozen in time. They found the remains of furnaces, their clay walls vitrified and stained from the intense, repeated heat. They discovered countless fragments of the ceramic crucibles that held the precious pigment mixture during firing. Analysis of these crucibles is particularly telling. Their interiors are often coated with a thin, glassy layer of the blue residue, a permanent record of their final use. But perhaps the most dramatic evidence comes from the waste itself. Heaps of production debris were found, including lumps of the fused, glassy slag that was the raw product straight from the kiln. Some of these lumps were a brilliant blue, while others were a failed greenish or blackish color, testament to the fine tolerances required and the batches that didn't quite meet the standard. This wasn't a clean operation, it was a gritty, industrial endeavor with waste materials simply discarded on site, giving us a direct sample of their successes and their failures. The scale of production becomes even more apparent at Qantir, the site of the great capital Pi Ramesses, built by Ramesses II in the Nile Delta. Here, excavations led by the German Archaeological Institute have uncovered what can only be described as an ancient industrial park. Vast workshop complexes were dedicated to crafting everything from faience and glass to, most importantly, Egyptian blue. The findings here are on a truly monumental scale. They uncovered large, well-constructed kilns capable of reaching and maintaining the high temperatures needed for hours on end. The volume of waste material is staggering: mounds of production slag, countless broken crucibles, and piles of grinding stones used to pulverize the cooled pigment cakes into powder. The presence of these grinding stones is crucial. They show the final step of the process was happening right there, turning the rough furnace output into a market-ready product. This evidence from Qantir and Amarna paints a picture of a highly organized, centralized industry. The production of Egyptian blue wasn't a casual side project for a potter. It required specialized knowledge, dedicated facilities, and significant resources. The state likely controlled the supply of key ingredients, especially the copper and the natron, and the workshops were probably attached to major temple or royal palace complexes. The artisans working these kilns were master craftsmen, their expertise passed down through generations. They understood the precise recipes, the subtle cues of temperature by the color of the flame, and the exact timing needed to produce a perfect batch. The archaeological record shows this wasn't a static technology either. Over centuries, the recipes and methods were refined, the kilns improved, and the production output increased to meet the massive demand from a culture that wanted to paint its entire world in the color of the gods. And so, this brilliant manufactured blue became far more than a mere decorative tool. It was a sacred substance, a physical conduit to the divine. In the worldview of the ancient Egyptians, colors were not passive, they held inherent power and meaning. Blue, in particular, was intrinsically linked to the heavens, the realm of the gods. Its association began with the most precious of stones, lapis lazuli, which was revered not just for its beauty but for its perceived cosmic significance. The deep blue stone, often flecked with golden pyrite that mimicked stars, was seen as a piece of the night sky itself, solid and eternal. By successfully recreating this color, the Egyptians believed they were capturing the very essence of the cosmos. They weren't just using a pigment, they were applying a piece of divinity onto their tombs, temples, and sacred objects. This profound symbolism is woven directly into their creation myths. In one of the most important cosmogonies, the world began from a primordial, infinite, and dark water known as the Nun. From these chaotic waters, the creator god Atum emerged on a mound of creation, bringing order to the universe. The scarab beetle god Khepri, who represented the morning sun and the concept of spontaneous creation, was often depicted as blue, his color symbolizing the life-giving waters of the Nile and the heavens from which he rolled the sun each day. Most significantly, the sky was personified as the goddess Nut, who was almost invariably painted in a stunning, deep Egyptian blue. She is shown as a woman arched over the earth god Geb, her body covered in stars forming the very vault of the sky. To paint her with this synthetic pigment was to literally build the heavens above the scene, reinforcing the cosmic order with every brushstroke. This celestial connection made Egyptian blue the obligatory color for depicting deities and the pharaoh, who was the living embodiment of the god Horus on earth. To visualize a god without their signature blue skin or blue headdress would be to deny their fundamental nature. Amun-Ra, the king of the gods, was often shown with a blue skin tone to emphasize his aspect as a primordial creator deity linked to the air and the hidden forces of creation. The ibis-headed god Thoth, patron of wisdom, and the falcon-headed Horus were also frequently rendered with blue crowns or bodies. For a pharaoh, being depicted in this hue was a direct claim to divinity. Statues of rulers, like the famous funerary mask of Tutankhamun, used lavish amounts of gold and Egyptian blue, the two most divine materials, to visually announce that this was no ordinary man, but a god-king whose rightful place was among the eternal stars. The blue on his headdress and beard wasn't just decoration. It was a declaration of his celestial authority and his promise of resurrection in the afterlife under the protective blue body of the goddess Nut. The brilliance of Egyptian blue was far too potent to remain a secret of the Nile Valley. Its fame, like the color itself, began to radiate outward, carried by trade routes and the tides of empire, until it became the undisputed premium blue across the entire Mediterranean world for more than 3,000 years. This was not a case of a simple product being exported. It was the transfer of a revolutionary technology, a secret recipe that was so valued, cultures adopted it even when they had their own sources of blue. Some of the earliest adopters were the Minoans on the island of Crete. As master seafarers and traders, the Minoans had extensive contact with Egypt. By the middle of the 2nd millennium BCE, they were not just importing jars of the finished pigment. Evidence suggests they had learned the recipe itself and were producing their own version. They used it to bring life to their breathtaking frescoes, like those in the Palace of Knossos, where blue dolphins leap through azure seas and blue monkeys climb across walls. The Minoans even put their own spin on it, sometimes adding a touch of cobalt to the mix, creating a slightly different shade that was uniquely their own. This demonstrates that the knowledge wasn't just copied, it was adapted and integrated into local artistic traditions. From the Minoans, the knowledge likely passed to the Mycenaeans on the Greek mainland and then spread throughout the Bronze Age world. But the true vehicle for its dominance was the rise of the Roman Empire. The Romans, with their insatiable appetite for luxury and color, encountered Egyptian blue and embraced it completely. They gave it a new name, caruleum, from the Latin word for sky or heaven, and its production became a major industry, with factories established in places like Pozzuoli near Naples. The Roman author and architect Vitruvius included a detailed description of its manufacture in his famous work De Architectura, a testament to its importance in Roman material culture. The demand was colossal. They used it to paint the walls of lavish villas in Pompeii and Herculaneum, creating breathtaking architectural vistas and intricate designs that still stun visitors today. They colored their sculptures with it, and there's even evidence they used it as a cosmetic, a truly extravagant use of a precious pigment. What's fascinating is that the Romans and the Greeks before them had access to their own local blue pigments. The Greeks had a lesser-known, rather dull cyan blue made from copper and calcium called Pozzuoli blue, yet they overwhelmingly preferred the vibrancy and stability of the imported Egyptian blue. This tells us that its superiority was immediately apparent. It wasn't just about color, it was about quality and prestige. Using Egyptian blue was a statement, a sign of wealth, taste, and connection to a wider, sophisticated world. Its journey from the royal workshops of the pharaohs to the villas of Roman patricians is a story of ancient globalization, a testament to how a truly groundbreaking innovation can transcend its origins to become a universal standard, uniting the ancient Mediterranean in a shared appreciation for a color that captured the very essence of the sky. This connection between the color blue and divine power meant its use was never casual. It was a calculated display of authority and wealth, a visual language understood by every subject of the pharaoh. To command the production and application of Egyptian blue was to demonstrate a godlike control over the very elements, turning common sand and stone into the substance of the heavens. It was the ultimate flex of royal power, and nowhere is this more brilliantly displayed than in the tomb of the boy King Tutankhamun. When Howard Carter first peered into the burial chamber in 1922, it wasn't just the gold that stunned the world, it was the dazzling, ubiquitous blue. The most famous object, his magnificent funerary mask, is a masterclass in this symbolism. The mask is primarily brilliant gold, representing the flesh of the gods, but it is intricately inlaid with stripes of deep blue glass and Egyptian blue pigment on the headdress and the ceremonial false beard. This wasn't just for aesthetic contrast, it was a deliberate pairing of the two most divine and valuable materials on earth, proclaiming the young king's divinity and his eternal reign in the celestial realm. The opulence continues throughout the tomb's contents. His inner coffinet, which held his organs, is a breathtaking sculpture of gold and blue glass. The inlaid blue stripes and patterns create a rhythmic, sacred geometry around the figure of the goddess Isis, who spreads her protective wings across the chest. Countless shabti figures intended to serve the king in the afterlife were fashioned from wood and then painted a brilliant blue or even carved from blue faience, a glazed ceramic that itself often used Egyptian blue as a coloring agent. His pectorals and broad collars, some of the most exquisite jewelry ever discovered, are mosaics of gold, carnelian, turquoise, and deep blue glass, all meticulously set to form patterns of scarabs and falcons. The message was unambiguous. In death, as in life, Tutankhamun was surrounded by, and indeed composed of, the sacred color of creation. Beyond the tomb, this royal command of the pigment was stamped across the entire landscape of Egypt. Temples, the literal homes of the gods on earth, were painted with vast quantities of Egyptian blue. Ceilings were a deep, star-studded blue, representing the body of the sky goddess Nut. Hieroglyphs spelling out the names and titles of pharaohs were often rendered in blue, ensuring their eternal utterance and power. On colossal statues and temple reliefs, the crowns of the pharaohs, the blue-striped Kepresh war crown or the solid blue Nemes headcloth, were painted with this pigment, a constant visual reminder that the ruler was the intermediary between the people and the blue, heavenly abode of the gods. This wasn't merely art, it was a form of political and theological propaganda. By controlling the sole production of this miraculous substance and lavishing it on their monuments, the pharaohs visually reinforced their divine right to rule. They demonstrated their ability to harness advanced, almost magical technology, and in doing so, they made the heavens themselves a permanent, tangible feature of their earthly authority. This legendary endurance of Egyptian blue, its ability to look as vivid today as it did the day it was applied, isn't just a happy accident. It is the direct, brilliant result of its synthetic, crystalline nature. To understand why it has triumphed over time, we have to understand what destroys other colors. Most ancient pigments were organic. They came from living things, plants, insects, or shellfish. Think of the rich purple from murex snails, the crimson red from crushed kermes insects, or the lush indigo from specific plants. The color in these pigments comes from complex organic molecules. And while these molecules are beautiful, they have a critical weakness: they are fragile. Their chemical bonds are vulnerable to the relentless energy of ultraviolet light from the sun. Over decades and centuries, this UV radiation breaks those bonds apart, a process we call photochemical degradation. It essentially bleaches the color molecule, causing the pigment to fade, sometimes into a dull, unrecognizable shade or even to vanish completely. Heat and moisture can accelerate this process, acting like a catalyst for destruction. Egyptian blue operates on an entirely different, far more robust principle. It is an inorganic pigment, a synthetic mineral. Its color doesn't come from a complex carbon-based molecule that can be easily dismantled. Instead, its power comes from its physical crystal structure and the metal ions trapped within it. As we discussed, those perfectly formed calcium-copper silicate crystals are its heart. The intense blue is a property of that specific lattice of atoms. The copper ions are locked into a rigid cage of silicon and oxygen, and this structure is held together by powerful ionic and covalent bonds. These are the same kinds of bonds that hold rocks and minerals together. The energy from sunlight, even after thousands of years of exposure, is simply not enough to break this mineral lattice. The crystal itself remains intact, and so the color remains perfectly preserved. It is, for all intents and purposes, a tiny man-made gemstone. This mineralogical identity also grants it incredible chemical stability. It is largely inert, meaning it doesn't readily react with other substances. Humidity, mild acids in the air, or even salts won't easily corrode it. This is the crucial difference between Egyptian blue and its natural mineral counterpart, azurite. Both are copper-based, but azurite is chemically vulnerable. When exposed to moisture and carbon dioxide over time, azurite undergoes a chemical transformation, converting into malachite, which is green. This is why you often see old European paintings where the Virgin Mary's blue robe has turned a murky green. The artist used azurite. Egyptian blue does not suffer this fate. Its stable silicate structure protects the copper ions from reacting with the atmosphere, locking that brilliant blue in place permanently. Furthermore, it is highly resistant to heat. Having been born in a 900°C furnace, it can easily withstand the ambient heat of a desert tomb or a Mediterranean summer. This combination of supreme lightfastness, chemical inertness, and thermal resistance makes it one of the most stable colorants ever created by human hands, ancient or modern. Its durability is a direct testament to the ancient Egyptians' profound understanding of material science. They didn't just create a color, they engineered a miniature artifact designed to survive for eternity. For over 1,000 years, the secret of Egyptian blue was lost, buried not in sand, but in time itself. The knowledge of how to create this radiant pigment vanished with the decline of the Roman Empire, and the color that had once painted the Mediterranean world faded into legend. It wasn't until the early 19th century, as a new wave of scientific inquiry swept across Europe, that this ancient technology was pulled back into the light. The first crucial steps in its rediscovery were taken by a pioneering chemist and adventurer, Sir Humphry Davy. Best known for his work with electrochemistry and his discovery of several elements, Davy was also deeply fascinated by the practical chemistry of the ancient world. During a journey to Italy in 1814 and 1815, he obtained samples of ancient blue paint from the ruins of Pompeii and from the baths of Titus in Rome. With meticulous care, he subjected these fragments to chemical analysis in his portable laboratory. Davy's methods were ingenious for their time. He used acids to dissolve the binding medium and isolate the pure color particles. He then observed how these particles behaved when heated, noting they fused into a transparent glass. Most tellingly, he conducted a flame test, a classic technique where a sample is heated in a flame to observe the color it produces. When he introduced his ancient blue samples to the flame, it burned with a brilliant green hue, the unmistakable signature of copper. Through these experiments, Davy correctly identified the key components, a glassy base of silica and an oxide of copper. He had successfully cracked the code, confirming that the stunning blue of the ancients was not a natural mineral but a manufactured substance, a copper-based synthetic. His work, published in 1815, was a landmark, shifting Egyptian blue from a myth into a documented historical technology and setting the stage for a century of further investigation. But Davy's analysis could only take the understanding so far. He identified the ingredients, but the precise crystalline structure and the exact chemical formula remained a mystery for another 100 years. The true revolution in understanding came with the development of powerful new analytical tools in the 20th century. The invention of X-ray diffraction, or XRD, provided the key. This technique allows scientists to peer into the atomic structure of a material by firing X-rays at a sample and analyzing the unique pattern of diffraction the rays create as they bounce off the atoms within the crystal lattice. When scientists like H.P. Stokes in 1934 applied XRD to Egyptian blue, the results were definitive. The diffraction pattern revealed a perfectly organized crystalline structure, confirming the pigment's identity as calcium copper silicate, and provided the precise measurements of its atomic arrangement. This was the final, incontrovertible proof of its synthetic nature. Later in the century, the scanning electron microscope, or SEM, added another layer of breathtaking detail. This instrument allowed researchers to see the pigment particles themselves, magnified thousands of times. For the first time, they could visually confirm what the chemistry had suggested. The pigment was indeed composed of those flat, rectangular crystals. The SEM images showed them in stunning clarity, revealing their size, shape, and how they clustered together. Even more advanced techniques like Raman spectroscopy allowed for non-destructive analysis, letting conservators identify the pigment on priceless artifacts without so much as touching them. These modern tools did more than just confirm an ancient recipe. They unveiled the sheer sophistication behind it. They showed that Egyptian blue wasn't a crude, accidental discovery. It was the product of a controlled, high-temperature process that produced a specific and complex crystal, a feat of materials science that we are only now fully able to appreciate with all our advanced technology. Armed with the precise chemical formula and a deep understanding of its crystalline structure, a new chapter in the story of Egyptian blue began, the quest to actually make it again. Knowing what it was wasn't the same as knowing how to create it. This is where the fascinating field of experimental archaeology took center stage. Researchers moved beyond the chemistry textbooks and into the workshop, determined to reverse engineer the entire process using only the materials and technologies that would have been available to an ancient Egyptian artisan. Their goal was not just to produce the color, but to truly understand the immense skill, intuition, and patience it required. The challenges they faced were immense. Modern recipes from textbooks were useless. They had to start from scratch just as the ancients did. They gathered their raw materials, quartz sand collected from the Nile Valley, chunks of green malachite ore, powdered limestone, and natron salt harvested from the Wadi Natron, the same ancient source the Egyptians used. They built replicas of simple pottery kilns, fueled not by gas or electricity, but by charcoal, learning through trial and error how to manage the airflow and fuel to achieve a consistent, scorching heat. The first attempts were almost universally failures. The mixtures would emerge from the kiln as a dull, greenish slag, a brittle black glass, or a crumbly, discolored mess. Without a thermometer, judging the temperature was a matter of painful experience, reading the color of the flames and the glow of the kiln's interior. The most critical variable they discovered was the precise window of temperature. Heating the mixture was a delicate dance. If the kiln was too cool, even by a 50 or 100 degrees, the chemical reaction simply wouldn't happen. The ingredients would just sit there unchanged, but if the kiln got too hot, soaring past 1,000 degrees Celsius, the entire mixture would melt into a homogeneous, runny glass that, upon cooling, was a transparent blue-green lump, a complete failure. The sweet spot was incredibly narrow, between 850 and 950 degrees, and it had to be held there for hours. Maintaining this soak time with a charcoal-fired kiln was a brutal test of endurance and attention, requiring constant stoking and adjusting of the vents. Researchers would spend entire days tending the fire, only to open the kiln and find another batch of useless greenish waste. Then there was the recipe itself. The ratios mentioned by Vitruvius, 1 part sand to 1 part copper and 2 parts natron, often produced poor results. Through painstaking repetition, modern experimenters found that the optimal ratio was far more nuanced. It required significantly more sand with a small, precise amount of copper and just the right amount of natron to act as a flux without making the mixture too alkaline. Grinding the ingredients to an extremely fine, uniform powder was also essential to ensure they reacted evenly. Each failed batch was a lesson, a piece of data pointing toward the right combination. The experimenters began to appreciate the immense tacit knowledge the ancient masters must have possessed, a knowledge not written down, but passed hand to hand through generations of artisans who learned to read the fire and feel the consistency of the grind. Finally, after countless attempts, a researcher would open a kiln, break open a crucible and find it, not a dull slag, but a solid, crystalline cake that, when fractured, revealed a deep, uniform blue core. The sound of grinding that cake produced a powder of breathtaking, vibrant azure. In that moment, a technological secret lost for over a millennium was truly reborn. And just when we thought we had unraveled all of its secrets, Egyptian blue revealed one more, a hidden property so extraordinary it has catapulted this ancient pigment straight into the forefront of 21st century technology. For millennia, its brilliance was something we could only appreciate with our eyes, but it turns out this man-made crystal had been emitting a different kind of light all along, a light completely invisible to us, just waiting for the right tools to reveal its glow. This phenomenon is called infrared luminescence, and its discovery has given archaeologists a kind of superpower. When a light source, like a simple LED lamp, is shone onto a surface painted with Egyptian blue, something fascinating happens. Our eyes see the reflected blue light, but the pigment itself also absorbs a portion of that light and re-emits it at a much longer wavelength in the near-infrared part of the spectrum. To our naked eye, this emitted light is completely invisible, but when viewed through a camera equipped with the right filter, something magical occurs. The Egyptian blue doesn't just appear blue, it appears to glow with an intense electric white light blazing out from the surrounding darkness as if it were lit from within. The power of this effect is not just in its visual spectacle, but in its incredible sensitivity. Over centuries, artifacts fade, crumble, and are overpainted. What looks to us like a blank patch of stone or a faded fragment of wood might still hold microscopic traces of this precious pigment, traces completely lost to the human eye. But to an infrared-sensitive camera, even a single tiny crystal of Egyptian blue can scream its presence. This has revolutionized the way we analyze ancient art. Conservators can now take a statue that appears to be bare, unadorned stone, scan it with this filtered camera, and suddenly see the ghostly white outline of a long-vanished blue crown or garment, revealing the original polychrome design that time had erased. They can examine a papyrus where the ink has faded to near nothingness and detect the faint, glowing signature of Egyptian blue used in an illustration, confirming its authenticity and age. This technique has been used to re-examine everything from Greek statues to Roman murals, proving that the ancient world was far more colorful than the monochromatic marble and stone we see in museums today. It's like putting on a pair of X-ray glasses that see only this one color, allowing us to peel back the layers of time and witness the artist's original intent in stunning, luminous detail. The implications of this discovery extend far beyond the museum, venturing into the realm of cutting-edge technology. The same property that makes Egyptian blue luminous so strongly, its efficient conversion of visible light into infrared radiation, is a holy grail in fields like medical imaging and telecommunications. Scientists are now studying the structure of these ancient crystals to develop new, highly efficient materials for use in modern devices. Researchers are exploring its potential in bioimaging, where its non-toxic, stable properties could be used to create new contrast agents that help light up specific areas of the body for diagnosis. There is even research into using it for security inks. A banknote or document could be printed with a pattern that is completely invisible under normal light but glows brightly under an infrared scanner, making it incredibly difficult to forge. It is a stunning full-circle moment. A technology pioneered by ancient Egyptian artisans 3,000 years ago is now inspiring a new wave of scientific innovation, proving that its potential is just as limitless today as the sky was created to represent. This leap from ancient art to modern science is one of the most thrilling chapters in the story of Egyptian blue. Researchers quickly realized that a substance which could so efficiently convert one kind of light into another was far more than a historical curiosity. It was a nanomaterial with incredible potential, a gift from the past to the future of technology. The key lies in those microscopic crystals and their intense near-infrared luminescence. This specific wavelength of light is incredibly useful because it can penetrate materials, including human tissue, with minimal scattering or damage, making it the perfect messenger for a host of advanced applications. In the field of biomedical imaging, Egyptian blue is paving the way for a new generation of contrast agents and biomarkers. Current imaging techniques often rely on fluorescent dyes that can be toxic, unstable, or require expensive and complex equipment to detect. But Egyptian blue is composed of calcium, copper, silica, and oxygen elements that are inherently non-toxic and biocompatible. Scientists have found that when they grind the pigment down to nanoparticles, these tiny crystals retain their powerful luminescent properties. Imagine injecting a solution containing these nanoparticles into the bloodstream. They could be designed to bind to specific types of cells, like cancer cells. When a surgeon then shines a safe, visible light onto the area during an operation, the nanoparticles would light up like miniature beacons in the near-infrared spectrum. The surgeon could use a special camera to see a real-time, glowing map of precisely where the tumor cells are, even distinguishing them from healthy tissue with incredible accuracy. This could revolutionize precision surgery, allowing for the complete removal of diseased tissue while preserving as much healthy tissue as possible. The ancient Egyptians created a color to guide the dead to the afterlife. Today, we are adapting it to guide surgeons in saving lives. Beyond the hospital, the unique signature of Egyptian blue offers a powerful weapon against counterfeiting. The global market is flooded with fake currency, forged documents, and counterfeit luxury goods costing economies billions. Modern security inks need a feature that is extremely difficult to replicate but easy for authorities to verify. The luminescence of Egyptian blue nanoparticles provides exactly that. A security tag or a pattern on a banknote could be printed using these particles. To the naked eye, it might look like a simple blue mark or even be completely invisible if mixed with other materials. But when a customs agent, bank teller, or store clerk waves a small, inexpensive infrared scanner over it, the hidden pattern would glow with an unmistakably bright signal. This is not a barcode or a QR code that can be photocopied. It is a physical property rooted in a specific crystalline structure that is incredibly difficult to reverse engineer and manufacture. The process to create these perfect crystals, which ancient artisans mastered over centuries, is a natural barrier to forgers. An art form once used to signify the divine right of pharaohs is now being used to protect the integrity of our most valuable modern assets, from passports to pharmaceutical labels. It is a profound testament to the enduring power of this ancient innovation, proving that a technology born in the fires of Egypt's kilns is still lighting the way forward. So how did such a revolutionary and widely used technology simply vanish? The story of Egyptian blue's disappearance is not a single event but a slow fading, a casualty of economic collapse, shifting artistic tastes, and the fragile nature of knowledge itself. Its decline began not with a bang, but with the gradual unraveling of the very systems that had nurtured it for millennia. The first and most critical blow was the decline of the ancient Egyptian state and its centralized, temple-based economy. For over 3,000 years, the production of Egyptian blue had been an industry overseen by and for the crown and the priesthood. It required organized mining for copper and natron, controlled distribution of these materials, and the maintenance of specialized workshops staffed by master artisans who passed their precise, unwritten recipes down through generations. This was not a hobby, it was a state-sponsored enterprise. As Egypt was successively conquered by the Persians, the Greeks under Alexander, and finally absorbed into the Roman Empire, this old, rigid economic structure began to erode. The Roman administration, while initially a major consumer of the pigment, eventually began to shift production to Italy itself, as Vitruvius's writings confirm. But this relocation may have diluted the deep, accumulated expertise. The knowledge wasn't just a recipe, it was a craft, an intuition for the fire and the grind that was honed over a lifetime. When the Western Roman Empire finally crumbled in the 5th century, the complex trade networks that supplied raw materials and distributed the finished pigment across the Mediterranean shattered. The large, stable market for luxury goods evaporated, and with it, the economic incentive to maintain such a specialized, resource-intensive industry simply collapsed. At the same time, the artistic and cultural landscape was transforming in ways that further marginalized the old Egyptian blue. The rise and eventual official adoption of Christianity within the Roman Empire brought with it a new aesthetic and a new set of symbolic priorities. The classical world's love for naturalistic murals, painted sculptures, and vibrant interior decoration gave way to a more symbolic and hieratic style of art, first in Byzantine mosaics and later in medieval iconography. While blue remained important, the source of that blue was changing. In the Middle Ages, a new champion emerged from the East, true ultramarine. This was the legendary pigment made from genuine lapis lazuli, now arriving through trade routes from the same Afghan mine. For the medieval church, the extraordinary cost of ultramarine was not a drawback but a feature. Its immense expense made it the ultimate act of pious devotion, a way to honor the Virgin Mary by lavishing her robes with the most precious substance on earth. This created a powerful new demand that Egyptian blue, now seen as an older, pagan material, could not fulfill. Furthermore, the recipe for manufacturing azurite pigment was refined in Europe. While still inferior in stability to Egyptian blue, azurite was more readily available in European mines and became the standard blue for many medieval and Renaissance painters. The world had moved on, and the unique niche that Egyptian blue had occupied for so long, a brilliant, affordable, mass-produced synthetic, was no longer there. Perhaps the most poignant factor in its disappearance was the loss of the knowledge itself. In an age before widespread literacy and standardized technical manuals, complex craft knowledge was stored not in books but in people. The exact temperatures, the subtle ratios, the specific type of sand, the look of the flame, the sound of the grind, this was tacit knowledge, passed from master to apprentice through years of hands-on practice. This kind of knowledge is incredibly vulnerable. It can be extinguished by a single generation that fails to pass it on. The political and social chaos that followed the fall of Rome, with its invasions, plagues, and economic disintegration, would have been more than enough to break these delicate chains of transmission. The artisans who knew the secrets may have found themselves without patrons, without materials, without apprentices, or simply without a peaceful place to practice their craft. The workshops fell silent, the kilns grew cold, and the precise alchemy required to turn sand into sky was forgotten. It became a legend, a color mentioned in old texts that no one alive knew how to recreate. The technology didn't fail, the society that supported it did, and the light of that particular knowledge was snuffed out, waiting over 1,000 years for a curious chemist with a new flame to coax it back to life. This remarkable synthetic crystal was far too versatile to be confined to a single use. The ancient Egyptians, in their characteristic ingenuity, found myriad ways to incorporate Egyptian blue into nearly every facet of their artistic and daily life. Its primary and most famous application was, of course, as a paint, but creating the paint was a process in itself. The fine blue powder straight from the grinding stone was useless on its own. It needed a medium to bind it to a surface, and the artists of the time had a whole pantry of options at their disposal. For painting on walls, whether the plastered surfaces of a tomb or a temple, they would typically mix the pigment with a tempera base, often using egg white or animal glue. This created a fast-drying, matte finish that was perfect for large, flat areas of color like a sky or a deity's skin. For more delicate work on wood, such as on a sarcophagus or a decorated chest, they might use a gum-based binder like gum arabic, which allowed for finer brushwork and a slightly more satin sheen. The process was meticulous. An artist would grind the pigment with a small amount of binding medium on a stone palette, adding water to achieve the perfect consistency before applying it with a reed brush to the prepared surface. The result was a layer of breathtaking color that, thanks to the pigment's stability, has survived in stunning condition where the organic binders themselves have not completely decayed. Beyond the flat canvas of a wall, Egyptian blue found a spectacular second life in the world of faience. Egyptian faience is not clay-based pottery. It is a unique material made primarily from crushed quartz sand, a small amount of lime, and an alkali like natron. Sound familiar? The recipe is strikingly similar to that of Egyptian blue itself, making the pigment a natural and perfect colorant for it. To create a faience object, craftsmen would mix the powdered ingredients with a little water to form a paste, which could then be molded into amulets, shabti figures, beads, or even cups. This paste was often pre-colored by mixing in a generous amount of Egyptian blue powder. The object was then fired in a kiln. During firing, the alkali would migrate to the surface and vitrify, forming a bright, glassy glaze, while the body of the object sintered into a hard, durable form. The result was a brilliant, self-glazing object of the most intense azure blue. This technique allowed for the mass production of sacred blue objects, from the protective eye of Horus amulets placed on mummies to the vast quantities of blue shabtis found in royal tombs, each one intended to serve the deceased in the afterlife. It was an ingenious way to make the sacred color of the heavens portable and accessible to many. Perhaps one of the most intimate and personal applications of Egyptian blue was in the realm of cosmetics. We know from analysis of residues in small containers and from artistic depictions that this prized pigment was sometimes used as a form of eye shadow. It would be mixed with a fat or oil base to create a creamy paste that could be applied around the eyes. This was not merely about vanity, it held significant practical and religious meaning. The coal-lined eyes we see in so many Egyptian portraits serve to reduce the sun's glare, much like the black grease used by modern athletes, but using blue pigment would have carried an additional, powerful symbolism. To outline one's eyes in the color of the gods was to invoke divine protection and perception. It was believed to ward off evil spirits and illnesses, and to allow the wearer to see with the clarity and power of a deity like Horus. Finding traces of Egyptian blue in a cosmetic pot reminds us that this was not some distant, abstract color used only for state art. It was a material that touched the very skin of the people, a daily reminder of their connection to the divine, a piece of the sky they could wear. Given the sheer complexity of the chemical process, how did ancient artisans working millennia ago achieve such stunningly uniform and consistent results without a single modern tool? They had no digital thermometers to monitor their kilns, no precision scales to weigh their ingredients, and no chemical manuals to consult. Their success was a triumph of meticulous observation, rigorous standardization, and a deeply ingrained craft tradition that treated the recipe as a sacred trust. The key to their consistency lay in a system of measurement and control that was remarkably sophisticated for its time. They likely relied on volumetric measurements using standardized ceramic vessels, a specific cup for the sand, a smaller dish for the copper ore, a known handful of natron. This ensured the ratios remained constant from one batch to the next. The ingredients themselves were sourced from very specific, known locations. The sand likely came from particular quartz-rich deposits, the copper from a trusted mine providing a consistent grade of malachite, and the natron from the same celebrated lakes in the Wadi Natron. This control over their raw materials eliminated a major variable right from the start. The firing process, which seems like the most unpredictable step, was mastered through generations of accumulated, hands-on experience. An experienced kiln master didn't need a thermometer. He could read the temperature by the color of the flames and the glowing interior of the furnace. A light orange glow indicated one temperature range, a bright yellow-white heat signaled another. They also used witness materials, small test pieces of clay or metal with known melting points placed inside the kiln. By peering through a viewing port and watching for when a specific test piece began to soften or glow, they knew the target temperature had been reached. Maintaining that heat was a physical skill, requiring constant feeding of the charcoal fuel and careful adjustment of air vents to control the oxygen flow. This was not a guessing game, it was a skilled performance, a dance with fire honed over a lifetime, ensuring each firing cycle replicated the conditions of the last. The role of the alkali flux, primarily natron, was absolutely critical and demonstrates a profound, if empirical, understanding of chemistry. Natron is a naturally occurring mixture of sodium carbonate and sodium bicarbonate. When added to the mixture and heated, it acts as a powerful flux. In simple terms, a flux is a substance that lowers the melting point of another material. Silica sand on its own has an extremely high melting point, around 1,700 degrees Celsius, a temperature far beyond what their simple kilns could reliably achieve. The natron intervenes by reacting with the sand, breaking down the robust silica network and forming a eutectic mixture. This is a specific combination of substances that melts at a much lower temperature than any of the individual components alone. By adding natron, the ancient chemists effectively tricked the sand into melting at a far more manageable 850 to 950 degrees Celsius. The flux also made the molten mixture less viscous, allowing it to flow more easily and enabling the copper ions to disperse uniformly throughout the melt, which was essential for growing those perfect color-producing crystals evenly. Perhaps the most delicate part of the entire process was controlling the oxidation state of the copper to ensure the signature blue hue. Copper is a fickle element. Its color changes dramatically based on its chemical environment. In a reduced state with limited oxygen, it can produce reds and purples. In a highly oxidized state, it can create green compounds like verdigris. The brilliant azure of Egyptian blue exists in a very specific intermediate oxidation state. The artisans mastered this by carefully controlling the atmosphere inside the kiln during the critical cooling phase. After the firing was complete, the kiln wasn't just thrown open. It was allowed to cool slowly, often over many hours, in a slightly reducing atmosphere, meaning the oxygen supply was restricted. This prevented the copper from becoming over-oxidized and turning the entire batch into a greenish slag. The slow cooling was also vital for the crystals themselves. It gave the calcium-copper silicate molecules the time they needed to arrange themselves into those orderly, flat, plate-like structures that are so effective at reflecting blue light. A rapid cooling would have resulted in a disordered, glassy mass with poor color. Every step from the sourcing of materials to the final slow cooling of the kiln was a carefully controlled variable in a magnificent 3,000-year-old chemical equation. Their precision wasn't born from instruments, but from an intimate, generational dialogue with the materials and the fire itself. To truly grasp the monumental achievement of Egyptian blue, we need to place it side by side with the other blues available to the ancient world. Each had its own story, but none could match the perfect combination of brilliance, durability, and accessibility that made the Egyptian synthetic the undisputed champion for over 3 millennia. First, consider the most prestigious of them all, a genuine ultramarine made from the precious lapis lazuli stone. This deep, celestial blue was mined from a single, remote source in the mountains of modern-day Afghanistan. Its journey to Egypt or the Mediterranean was an epic undertaking, transported thousands of miles along perilous trade routes. This immense distance and difficulty made it phenomenally expensive, a luxury item reserved for adorning the eyes of statues of the most important gods or for tiny, intricate details on the jewelry of pharaohs. But the expense didn't end with acquisition. To turn the rough, dark blue rock into a usable paint was an incredibly labor-intensive process. The stone had to be carefully crushed and then ground by hand. This powder was then mixed with a paste of wax, resin, and oil and submerged in a weak lye solution. Artisans would knead this mixture for days repeatedly, gently washing out the blue pigment particles which separated from the unwanted gray rocky material. It could take weeks of work to produce a single ounce of the finest grade ultramarine blue. This was a color of almost unimaginable value, so costly that its use in Renaissance Europe centuries later was often stipulated in painting contracts and paid for by wealthy patrons separately from the artist's fee. Egyptian blue offered a way to achieve a similar visual impact without the crippling expense and backbreaking labor, making the color of the heavens available on a scale that lapis lazuli simply never could. Then there was azurite, a copper carbonate mineral that offered a softer, lighter sky blue hue. Unlike lapis, azurite was more widely available, with sources across Europe and the Mediterranean, making it a more common choice for painters in many ancient cultures. But azurite came with a devastating flaw: it was chemically unstable. The mineral is highly susceptible to a process called oxidation when exposed to moist air. Over time, the copper carbonate slowly reacts with water and carbon dioxide, transforming into basic copper carbonate, which we know as malachite, a green mineral. This meant that a beautiful azure sky painted on a fresco or the blue robe of a sacred figure would gradually, inevitably turn a dull, sickly green. We see this tragic transformation in artworks throughout history. Many medieval and Renaissance paintings of the Virgin Mary, originally rendered in a brilliant azurite blue, now show her robes as a murky, muted green. This inherent vice made azurite a risky choice for any work intended to last. Egyptian blue, by contrast, was a triumph of stability. Its synthetic silicate crystal structure locked the copper ions in place, making it virtually impervious to the atmospheric conditions that doomed azurite. An artist choosing Egyptian blue could be confident that their work would remain true for centuries, not slowly degrade before their eyes. The final category of ancient blues were the organic dyes, derived from plants like woad or insects. These could produce beautiful, vibrant colors, but they suffered from a fatal vulnerability. They were fugitive. The complex organic molecules that give these dyes their color are easily broken down by the energy in ultraviolet light from the sun. A textile dyed with an organic blue, or a painting using it as a pigment, would fade dramatically over a relatively short period, often leaving behind only a faint, ghostly trace of the original hue. They were the opposite of eternal. They were ephemeral by nature. Egyptian blue's inorganic, mineral-based identity made it the ultimate solution to this problem. Its light fastness was supreme. This comparison reveals why Egyptian blue was so revolutionary. It wasn't just another option on the palette, it was a complete package. It offered the visual intensity of the most precious stone without the exorbitant cost, the availability of a common mineral without its tragic instability, and the potential for mass production that no organic dye could ever promise. It was, quite simply, the perfect ancient pigment, a solution to every artistic and practical problem that the color blue had ever presented. The production of Egyptian blue was never just an artistic pursuit. It was a major industrial and economic engine, a complex enterprise that reached from the most remote deserts to the bustling ports of the Mediterranean. Its creation required a secure and consistent supply of raw materials, and the mechanisms put in place to acquire them reveal a highly organized state economy. The quest for copper, the essential coloring agent, drove mining expeditions deep into the eastern desert and the Sinai Peninsula. These were not small-scale operations. At sites like Timna and Serabit el-Qadam, archaeologists have found extensive ancient mining networks, complete with thousands of stone hammers, grinding stones, and slag heaps that testify to centuries of intensive labor. Securing these outposts was a matter of national importance, often requiring military protection for the miners and engineers who braved the harsh, arid conditions to extract the precious green malachite ore. The state, in the form of the pharaoh and his administration, almost certainly controlled these mining operations, treating copper not just as a metal for tools and weapons, but as a strategic resource for cultural and religious expression. Equally vital was the procurement of natron, the alkali flux that made the entire chemical reaction possible. This was harvested from the dried lake beds of the Wadi Natron, a valley northwest of Cairo that became one of the most important chemical resource sites in the ancient world. The harvesting of natron was a seasonal activity, likely carried out by specialized work crews who would collect the crusts of salt that formed on the lake beds and transport them back to the river valley. The state's control over this resource is underscored by its other primary use, mummification. The same natron used to dry and preserve the bodies of the elite was also used to flux the silica in the blue pigment workshops. This dual sacred purpose meant that the production and distribution of natron were tightly managed, adding another layer of centralized economic control to the pigment's manufacture. The transformation of these raw materials into the finished product happened in specialized workshops, which functioned like ancient industrial factories. As we saw at Kantir and Amarna, these were not small pottery kilns run by a single family. They were large, dedicated facilities with multiple furnaces, grinding stations, and areas for sorting and packaging. The artisans working here were highly skilled state employees, their knowledge a valuable and protected asset. The economic model was likely one of royal or temple patronage. The state supplied the raw materials, the copper, the natron, the fuel, and the workshops produced the pigment, which was then allocated for state projects, the decoration of temples, royal tombs, and official monuments. This system created a class of specialized craftsmen whose entire livelihood was tied to this one product, fostering an environment where technical knowledge could be refined and perfected over generations. But the economic impact of Egyptian blue extended far beyond Egypt's borders. The finished product itself became a highly valuable export commodity, traded throughout the Mediterranean world. While the state likely controlled its production, merchants would have been responsible for its distribution. Jars of the fine blue powder would have been shipped north along the coast of the Levant to the Minoans on Crete and later to the Greek mainland. The value was not merely in its beauty but in its technology. For cultures that acquired it, Egyptian blue represented access to a color they could not reliably produce themselves. Its trade would have been a lucrative business, adding to the wealth and prestige of Egypt. In a very real sense, Egypt was not just exporting a color, it was exporting a piece of its advanced technological identity, a tangible symbol of its cultural sophistication that was in demand from every corner of the ancient world. This thriving trade network helped to weave Egypt into the economic fabric of the Mediterranean, establishing it as a center not only of mystical power but of material innovation and commerce. Today, a dedicated community of historians, artists, and materials scientists has taken on the ultimate challenge: to walk in the footsteps of those ancient masters and bring Egyptian blue back to life using only the tools and materials that would have been available thousands of years ago. This isn't just about replicating a color, it's a profound act of experimental archaeology, a hands-on quest to understand the minds of the first chemists by physically recreating their greatest triumph. The process begins not in a laboratory but in the field with a painstaking search for authentic raw ingredients. Modern practitioners journey to the very sources the Egyptians used, gathering quartz sand from the Nile Valley, seeking out green malachite ore from known ancient mining areas, and harvesting natron salt from the sun-baked lake beds of the Wadi Natron. This initial step is crucial as the specific mineral composition of these materials can dramatically affect the final outcome. A sand with too much iron impurity, for instance, can lead to a muddy, unsuccessful batch. This reliance on natural, unrefined sources means that every new attempt carries an element of unpredictability, a direct connection to the challenges faced by the original artisans. The real test, however, comes at the kiln. Without the aid of modern pyrometers, artists must learn to read the fire itself. They build replicas of simple, open-topped pottery kilns fueled by charcoal and spend hours meticulously managing the fuel and airflow. The goal is to achieve, and more importantly, maintain that narrow window of scorching heat between 850 and 950 degrees Celsius for a sustained period. This is a physically demanding and often frustrating process. Many attempts result in failure. A kiln that doesn't get hot enough produces a crumbly, unreacted mass, while one that gets too hot melts everything into a homogeneous, runny blue glass that lacks the desired crystalline structure. The first sign of success often isn't even visual, it's the sound. When the cooled, glassy slag cake is broken open, a successful core will have a distinct crystalline fracture. Grinding that cake with a stone mortar and pestle produces a specific, gritty sound that experienced recreators learn to recognize, a hopeful sign before the powder even reveals its color. One of the most significant revelations from these modern experiments is the critical importance of the alkali flux. While ancient texts like those of Vitruvius provide a basic recipe, modern practitioners have found that his suggested ratios often fail. Through relentless trial and error, they have discovered that the optimal recipe is far more nuanced, requiring a much higher proportion of silica sand to copper, with just the right amount of natron to act as a flux without making the mixture too alkaline. This fine-tuning is a testament to the deep, tacit knowledge the ancient Egyptians must have possessed, knowledge that was never written down but was learned through a lifetime of hands-on experience. Artists like those at the Pigment Compendium or working with institutions like the Getty Conservation Institute have documented their journeys, sharing their many greenish failures and their rare, breathtaking successes. When they finally pull a brilliant blue cake from the kiln and grind it into a powder of stunning, vibrant azure, they experience a moment of profound connection across the millennia. They haven't just made a color, they have successfully reverse-engineered a lost technology, proving that the genius of the ancient Egyptian chemists was not a myth, but a reproducible, tangible reality. This industrial-scale production of Egyptian blue, for all its brilliance, did not leave the landscape untouched. The quest for this celestial color had a very terrestrial cost, an environmental footprint that we can now trace through the archaeological record. To understand the full scope of this ancient industry, we must look beyond the workshops and kilns to the sources of its raw materials and the fuel that powered its creation, painting a picture of an early industrial activity that reshaped local environments. The most visible impact began at the source, the mines. The relentless demand for copper, the essential coloring agent, drove extensive mining operations in the Eastern Desert and the Sinai Peninsula. These were not small, shallow pits. At sites like Serabit El Qadim and Wadi Maghara, miners dug deep tunnels and large open-cast quarries to extract the malachite and copper ore. This process was incredibly destructive to the immediate landscape. Vast quantities of rock and earth were removed and piled into massive spoil heaps that still scar the terrain today. The mining process itself required immense amounts of water for dust suppression and for the initial stages of ore processing, a precious resource in the arid desert environment. Furthermore, the furnaces used for preliminary smelting of the copper ore right at the mine sites consumed huge amounts of local timber, likely contributing to deforestation in these already fragile ecosystems. The operation of these remote mines also required supporting communities of workers, whose need for food, water, and shelter placed additional strain on the local environment. The procurement of the other key ingredient, quartz sand, also had its consequences. While sand was abundant, not just any sand would do. The ancient artisans needed a clean, high silica sand, free from contaminating clays and iron oxides that could muddy the famous blue hue. This suggests they sought out specific, pure deposits, possibly from particular locations along the Nile or from desert sources. The quarrying of this sand, even if on a smaller scale than mining, would have altered those local areas, removing vegetation and topsoil to access the underlying strata. The grinding of this sand, along with the limestone and the final pigment cake, required tough, durable grinding stones made from specific types of rock like granite or basalt. The quarrying and shaping of these heavy tools represented another layer of resource extraction, another demand on the environment to support this vast industrial chain. Perhaps the most significant environmental cost was the insatiable appetite of the kilns themselves. Maintaining a temperature between 850 and 950 degrees Celsius for hours on end required a phenomenal amount of fuel. For a large workshop center like the one at Cantia, producing pigment on an industrial scale, the demand for fuel would have been constant and colossal. The primary fuel was charcoal, which is made by slowly burning wood in a low-oxygen environment. This process is incredibly inefficient, requiring vast quantities of wood to produce a much smaller amount of charcoal. To feed the furnaces of the Egyptian blue industry, entire forests of acacia and thorn trees along the Nile Valley and its margins would have been harvested. This large-scale deforestation would have had cascading effects: loss of habitat for wildlife, increased soil erosion along the riverbanks without tree roots to hold the earth in place, and a potential contribution to local climate change by reducing shade and moisture retention in the area. The sheer scale of production, evidenced by the massive slag heaps at Cantia, points to an industry that fundamentally altered the energy economy of its region, drawing down ancient woodlands to fuel the fires of creation. Yet, it is crucial to view this environmental impact through an ancient lens, not a modern one. The Egyptians of the New Kingdom were not heedless polluters. They were a society deeply connected to and dependent on the natural cycles of the Nile. Their impact, while significant, was ultimately localized and on a scale that the ecosystem could, over very long periods, recover from. There is also evidence that they practiced a form of resource management, perhaps even cultivating fast-growing trees like acacia in groves to ensure a sustainable supply of wood for charcoal. The legacy of Egyptian blue is thus a complex tapestry. It is a story of breathtaking human ingenuity and artistic achievement, but also one of early industry's inevitable trade-offs. It reminds us that the creation of beauty, even a beauty meant to honor the gods and the heavens, has always required a transformation of the earth, a negotiation between human ambition and the resources of the natural world. While the direct production of Egyptian blue ceased in the West, its ghost continued to haunt the artistic imagination of later cultures. The knowledge of how to create the specific calcium-copper silicate crystal was lost, but the fundamental principle of using copper and an alkali flux to produce a brilliant blue was a technological seed that found fertile ground elsewhere. One of the most spectacular flowerings of this legacy can be seen in the magnificent glazed ceramics of the Islamic world, particularly from the 9th century onward. Islamic potters, building upon centuries of glassmaking and ceramic traditions from Persia and Mesopotamia, achieved a revolution in lusterware and tin glazing. But for the color blue, they turned to a technique with a familiar echo. They created stunning cobalt blue decorations on a white tin-glazed background, but they also developed a range of turquoise and greenish blue glazes that were fundamentally copper-based. The process was different, applying a copper oxide colorant to a pre-formed clay body and then covering it with a clear glaze before a single firing. But the core chemistry was a direct descendant of the ancient Egyptian principle. The vibrant turquoise tiles that adorn mosques and palaces from Samarra to Isfahan, shimmering in the sun, are a spiritual successor to the Egyptian blue that once covered the tombs of pharaohs. They represent a parallel evolution of the same idea, proving that the quest to master copper's potential for creating celestial blues was a continuous thread in human history. This influence traveled along trade routes into Europe, where it helped to ignite a ceramic renaissance. In the late Middle Ages, Spanish potters in Valencia, living under Muslim rule, began producing what became known as Hispano-Moorish ware. They used the tin glazing techniques of their Islamic neighbors and frequently featured brilliant cobalt blue designs. As this style spread to Italy, it evolved into the tradition of Maiolica. Italian Renaissance artists, using these bright white, blue-decorated ceramic plates and plaques as a canvas, created intricate narrative scenes. While the most prized blue pigment for these fine art paintings was the astronomically expensive ultramarine, the blue used for the ceramic backgrounds and borders was a more accessible cobalt or copper-based glaze. The very existence of this vibrant medium, which allowed for such expressive work, was indebted to a technological lineage that stretched back through the Islamic world to the ancient Egyptians. The blue might not have been the exact same compound, but the artistic freedom it provided, the ability to bring a permanent, sky-like brilliance to a durable object, was a direct continuation of the revolution Egyptian blue had started 3,000 years earlier. Perhaps the most fascinating legacy, however, lies in the world of painting itself. After the fall of Rome, European artists were left with a limited palette for blue. They had azurite, which was affordable but prone to turning green, and they had the sublime but impossibly costly ultramarine. For centuries, the quest for a stable, synthetic blue to rival the ancient worlds was a holy grail. Then, in the 18th century, a breakthrough occurred in Germany. A color maker named Johann Jacob Diesbach, while attempting to create a red lake pigment, accidentally produced a startlingly intense blue. This new color, first known as Berlin blue and later as Prussian blue, was iron-based, not copper-based, but it shared the same revolutionary characteristic as Egyptian blue. It was synthetic, reproducible, and relatively affordable. Its invention marked the beginning of a new age of color chemistry. In the early 19th century, as chemists began to scientifically analyze ancient pigments, they identified the composition of Egyptian blue. This rediscovery did not lead to its commercial revival, as Prussian blue and other new synthetics had already taken hold, but it did something just as important. It revealed that the ancients had already achieved what European science was only just beginning to master. The invention of Prussian blue and its successors can be seen as the modern world finally catching up to an idea that had its genesis in the kilns of ancient Egypt. The legacy of Egyptian blue, therefore, is not just in the specific color itself, but in the very concept of synthetic pigment creation, a testament to humanity's enduring desire to conquer the palette and engineer the colors of their dreams. For all its legendary durability, the task of conserving artifacts adorned with Egyptian blue presents a fascinating and delicate paradox for modern museum professionals. While the pigment's crystals are defiantly stable against light and time, they can be surprisingly vulnerable to the very processes designed to preserve them. This creates a complex conservation challenge where the goal is not to fight decay, but to understand and respect the intricate weaknesses of a material that has already survived millennia. The primary threat to Egyptian blue in a museum setting is not the environment but us. Many common cleaning methods used to remove centuries of grime, dirt, and salts from artifacts can inadvertently damage or even strip away this precious pigment. Water, the most basic tool in a conservator's kit, can be a problem if it's too acidic or alkaline. The binder, the ancient egg white, gum, or glue that holds the pigment to the surface, is often fragile and water-soluble. Applying an aqueous solution to clean the surrounding stone or wood could inadvertently dissolve this ancient adhesive, causing the brilliant blue powder to simply brush away or run down the surface, irrevocably losing the artist's work. This sensitivity extends to a range of chemical cleaning agents. Solvents that are perfectly safe for the underlying limestone of a statue might interact poorly with the copper ions in the pigment, potentially altering its crystalline structure or leaching the copper out, which would leave behind a faded, washed-out husk of its former glory. Even mechanical cleaning, the gentle use of scalpels, brushes, or micro-abrasives under a microscope carries a risk. The pigment particles, though hard, are only loosely bound to the surface by the aged adhesive. An overly enthusiastic touch with a soft brush could be enough to dislodge a shower of irreplaceable azure crystals. Therefore, the first and most critical step in any conservation project is rigorous analysis. Before a single tool is picked up, conservators use non-invasive techniques to map the presence of Egyptian blue. They might use portable X-ray fluorescence to detect the copper signature, or, most effectively, use an infrared camera to make any trace of the pigment glow brightly, revealing its exact distribution and helping them avoid those areas entirely during cleaning. Beyond the technical challenges lie profound ethical considerations. Every decision a conservator makes is a permanent intervention. The central question is always, how much should we clean? Should we remove the white haze of salts that have crystallized on the surface over centuries, even if they are now part of the object's history? Should we try to return the blue to its original electric vibrancy, or is the muted tone it has acquired over time a valid part of its aged character? There is a growing philosophy in conservation that favors minimal intervention. The goal is not to make an artifact look new, but to stabilize it for the future while preserving every possible bit of its historical narrative, including the visible passage of time. This often means making peace with imperfection. A conservator might choose to clean only the most damaging grime, leaving a faint shadow of dirt around the blue areas to ensure not a single crystal is lost. They might apply a microscopic consolidant, a stable, modern synthetic resin not on top of the pigment, but injected behind it to re-anchor it to the surface without altering its appearance. The work is a painstaking ballet of science and ethics, where the highest achievement is to be invisible, ensuring that when we look upon an ancient blue ibis or a pharaoh's headdress, we are seeing as much of the original as possible, protected and preserved for the next 3,000 years. Even with our modern tools unraveling so many of its secrets, Egyptian blue continues to pose profound questions that push the boundaries of both archaeology and materials science. One of the most active areas of research focuses on whether this technology was a single, monolithic recipe or if it evolved into distinct regional variations as it spread across the ancient world. We know the Minoans on Crete were producing it, but were they simply copying an Egyptian formula, or did they adapt it to local materials and tastes? Advanced spectroscopic analysis is now being used to compare samples from Egypt, Mesopotamia, the Greek islands, and Roman sites. The goal is to detect subtle chemical fingerprints, trace elements in the sand, slight variations in the copper ore, or different alkali sources that could act like a geographic signature. Finding these differences would revolutionize our understanding of ancient technology transfer. It would suggest that cultures weren't just passive recipients of a finished product. They were actively experimenting, tweaking the recipe based on what materials they had available, and putting their own innovative spin on this ancient wonder. This turns the narrative from one of simple diffusion into a story of collaborative, international scientific development spanning millennia. This leads directly into another tantalizing mystery: the exact pathways of how this complex knowledge traveled. We see the pigment appear in different places, but how did the know-how get there? Was it transferred through the movement of skilled artisans themselves, perhaps gifted from one pharaoh to another as a diplomatic gesture? Or was it conveyed through detailed written instructions on papyrus scrolls or clay tablets that have long since turned to dust? Perhaps the knowledge was passed through more informal channels, like traders describing the process in broad terms, leaving local craftsmen to spend years reverse engineering it through trial and error, which might explain the evidence for failed batches found outside of Egypt. The search for answers is driving linguists and historians to re-examine ancient texts with a new focus, looking for any passing mention of blue makers or the exchange of craftsmen. It's a difficult puzzle because this kind of tacit, hands-on knowledge is rarely written down in detail. The transfer of Egyptian blue's recipe may represent one of the earliest and most significant instances of intellectual property exchange in human history, and we are only now beginning to trace its contours. Perhaps the most forward-looking field of research asks not about the pigment's past, but about its future potential. Scientists are now treating Egyptian blue not as an artifact, but as a novel nanomaterial with properties we are only beginning to comprehend. Its incredibly strong near-infrared luminescence has already revolutionized art conservation, but that might just be the beginning. Researchers in bioengineering are investigating its potential as a non-toxic imaging agent. Imagine if these ancient crystals, ground down to nanoparticles, could be injected into the human body. Their ability to glow brightly under infrared light could help surgeons visualize the boundaries of tumors with incredible precision, lighting up cancer cells while leaving healthy tissue dark. Other teams are exploring its use in new types of security inks for printing currency, where a pattern made with Egyptian blue nanoparticles would be completely invisible to the naked eye, but would blaze unmistakably under a simple infrared scanner, making counterfeiting virtually impossible. There are even experiments into incorporating it into advanced optical materials for telecommunications and computing, where its efficient light conversion properties could be harnessed to transmit data. Each of these applications stems from a fundamental question: what other secrets does this crystalline structure hold? The ancient Egyptians created it to mimic the heavens, but they may have inadvertently engineered a material that will shape the technology of tomorrow. So as our journey through the story of Egyptian blue comes to a close, we're left with a remarkable realization. This was far more than just a pretty color. What the ancient Egyptians achieved in their sandy workshops was, in every meaningful sense, one of humanity's first and most successful forays into nanotechnology. They were not merely mixing paints, they were engineering matter at a microscopic level. By meticulously controlling heat and chemical reactions, they coaxed raw materials into forming perfect flat crystals, each one a tiny, self-contained light filtering machine designed to perform a single, brilliant task with flawless efficiency. This level of control over the molecular structure of a material is the very definition of sophisticated materials science, and they were doing it over 4,500 years ago without a single modern instrument to guide them. It stands as a powerful testament to a civilization we are still struggling to fully appreciate, one whose technological prowess was every bit as advanced as its architectural and spiritual achievements. The legacy of this innovation stretches across the ages in the most unexpected ways. It's a story that connects the artisans of the Nile Valley to the painters of Pompeii, and now, astonishingly, to the scientists in modern laboratories. The same crystalline structure that gave a statue of Osiris its vibrant hue is now being studied for use in biomedical imaging, helping surgeons distinguish healthy tissue from diseased cells. The pigment created to adorn the tombs of pharaohs is now being ground into nanoparticles to create unforgeable security inks for modern banknotes. This is the ultimate validation of their genius, a technology that was ahead of its time not just by centuries but by millennia. It's a beautiful, full-circle moment where the past is actively informing the future, where an ancient solution is providing answers to modern problems we are only just beginning to understand. This incredible journey from a kiln in ancient Egypt to a cutting-edge lab reminds us that human curiosity and ingenuity are timeless. It challenges the arrogant notion that technological progress is a straight, upward line, and instead shows us that brilliant ideas can be lost, found, and then rediscovered again, each time offering new lessons. The story of Egyptian blue is a humbling and inspiring reminder that the drive to create, to improve, and to understand the world through science and art is a fundamental part of who we are. It connects us to those ancient chemists who stared into a furnace and saw not just fire, but the potential to capture a piece of the sky itself. We would love to hear which ancient technology captures your imagination. Is it the Roman concrete that strengthens with time, the mysterious Antikythera mechanism, or something else entirely? Share your thoughts in the comments below, and thank you for exploring this amazing slice of history with